Hello, everyone. Welcome back to the AAS YouTube channel, and this is part of the good stuff. This is the AAS Journal Author Series, and I'm very happy to have Grigori Fedorets with us today. Hi, Grigori.
Hi, Frank. How are you?
I am doing well on this coming up on near winter solstice well, I should just say solstice, because if I was in another hemisphere, I wouldn't be calling it winter. So we'll just call it solstice. What's your geolocation, Grigori?
Well, I am currently sitting in Helsinki, Finland, although I do work in Queen's University Belfast.
Okay. So in Finland, excuse my geography here, are you above the Arctic Circle there?
Not quite. It's the 60th degree latitude. So
okay. So you still get
5 degrees.
Okay.
More, and we would be at that.
Okay. So the days are still short right now.
Yes. Yes. Very dark.
Very dark. Snow?
No whatsoever.
Really?
Very dark indeed. No. Yeah. Just rain. Very rainy. Very dark.
Okay. Is that normal, or would you normally expect snow this time of year?
It's a little. We would expect it a little more to the north. So it's quite. We're used to it already by now. Oh.
Okay. So how is so are you in Finland, but you're at Belfast because of the current pandemic, or is there some arrangement?
Yeah, just time for Christmas.
Got it. Right. Solstice. Very good. Very good. Awesome. Grigori, what do you like to do for research?
I study the small bodies of the solar system, and in particular, I study these objects called minimoons, which we're going to talk about in a short while. I also currently work a little with the upcoming Rubin Observatory's legacy survey of space and time, preparing for that with the solar system research, and I also tap a little on the Gaia mission, also with the solar system objects.
Cool, very nice. And that will bring us to this really lovely article. This one is an AJ, Astronomical Journal, and we have Establishing Earth's Minimoon Population Through Characterization of Asteroid 2020 CD3. And Grigori, take us away.
Thank you, Frank. So the first thing I would like to say that this is really a group effort. As you can see, quite a long list of authors over there, and they all have made a significant contribution to this work. Before we go into the paper, let me say a couple of words about what minimoons are. Mm-hmm. So minimoons are essentially asteroids which become temporarily captured within a planet system. Okay. We know that they are possible to make these temporary captures for all solar system planets, and the most famous one has been for Jupiter, the famous comet Shoemaker-Levy 9, mm-hmm. which it was captured around in the 1920s, and then it crashed into Jupiter in 1994. And in 2006, the first asteroid, 2006 RH120, was discovered on a geocentric orbit, the first of its kind, and it was described in a paper by Kwiatkowski et al. In 2009. Mm-hmm. And after that, it was realized that there is actually a population of these objects through theoretical work by Mikhail Gravnik et al. And after that, we have been waiting for the next minimoon to be discovered. And this happened in earlier this year. I'll go to that in a little while. But before that, let me just say a few words. Why would it be worth studying minimoons? So I can think of maybe three primary reasons. Well, first of all, they're quite small. So they are, this object we're talking about in an asteroid with a diameter of 1.2 meters. The previous one was a diameter of 3 meters.
Mm-hmm.
So these are essentially these kind of boulders, rocks, which, we don't really know. They're numerous, but they're not very well studied because they're so faint and quite hard to detect. So we don't know much about them. And these objects, since they become captured, they spend quite a significant amount of time in the vicinity of Earth. So if we would like to study the population of these objects, they provide the best opportunity for that. Second of all, they help to resolve the size frequency distribution of near Earth asteroids in the 1 to 10 meter regime. So they are. This is it's currently a study under interested this population because if you remember the Chelyabinsk meteorite, it was 17 meters, a little larger than these ones, but they're kind of in terms of for example, the impact hazards, they are the ones that are more numerous and cause a lot of damage in that sense. Even more so on our life scale, they cause more damage than the big ones, the super catastrophic ones.
Right.
And the third one, probably my favorite one, is again, since they are quite close to the Earth for a quite long time, they are the best targets for in situ exploration. So we could send a spacecraft and study them for free, essentially, because they're so close to the Earth. We don't need so much fuel.
Cool.
And that's for everybody's happy when something is cheaper than when it's expensive. Okay.
Indeed.
All right, so that's my background, and let's go to take a look at the paper. So here let's talk about the discovery circumstances of 2020 CD3. Like the first one, it was discovered by the Catalina Sky Survey, which is a part of University of Arizona by our co-authors Kacper Wirtz and Theodor Pruin. And on the next day, it was calculated by the JPL Scout system that it was indeed on a geocentric orbit. Cool. It is always suspicious when an object is on a geocentric orbit. The first question we get, is this real? Is this artificial, or is this real? Because as we all know, there are a lot of satellites and debris on the geocentric orbit, and more are coming. So, unfortunately, yes. So how do we distinguish between these? There are a couple of ways, but the most important one is looking at the area to mass ratio of objects. So essentially, we fit, instead of a 6-parameter Keplerian orbits like in AEI omega m, we fit the seventh parameter, which is the area to mass ratio. Essentially, when you fit an orbit, you see a slight displacement from the purely gravitational orbit, and when you fit that, you can see how much it is displaced, especially for these very small objects. And this is what we can see at figure 1. This is a evolution of the area to mass ratio as a function of time since discovery. So on the y-axis, you can see that the unit is meters squared per ton, and the x-axis is the time since discovery. So the artificial objects start from going up from around 3 units and going higher, higher, higher. And below 1, it's a regime of natural objects. So as you can see, as the time evolved, the area to mass ratio of 2020 CD3 became smaller and smaller and smaller before we could actually say that, okay, at around 20 days, we're quite certain that it is natural, and at 35, it was already, well, that was very certain there. Yeah, and one thing maybe worth mentioning is that this is a very subtle effect, and this kind of precision work has been enabled by the accuracy which is provided by the Gaia mission's second data release 2. So cool. This kind of okay, so that is about the discovery circumstances, and this is one of the main this is the main evidence that we have that this is a natural object. We have more though. So if we go further on, and let's take a look at the next image, next plot. I think it's.
Yep, here we go.
Yep. So here we can see, if we take a look at figure 2A, this is the reflectance spectrum of the asteroid obtained with the Gemini North Observatory. So from this, we can see, so there are four main asteroid classes in this case. So there are the Cs, which are the blue ones. This is the flat line. Yeah, that one. That is essentially the carbonaceous, the primitive ones. Then we have the X types, the yellow ones. That is, we think that is like metallic types. And then the S, and then there are the S and the V type, the turquoise and the green one, which are they're the silicate ones. So, and the V type, and so from this plot we can see that we can't really so the black images are the photometric points in the Sloan GR and I. There is also another paper by Bryce Bolin et al. That they have made observations with the Keck Observatory. They also got the Z band, and there they show that it is more resembling the V type. So, but yeah, we didn't get it. So here we speculate. Our results show it's either it's S or V, but now we know it's actually a V, thanks to other observations by Bolin et al. Okay, so that is the second piece of evidence. You may ask, how do the artificial objects fit in this picture? So actually, they are even more redder. So if you take a look at the reflectivity, the y-axis on 2A, in the I band at around something 8,000 angstroms, it would be closer to 1.6 or 2. So it would be the slope would be even much higher. So
okay,
for those that we know, so that's the second piece of evidence that we know that is a real object. And then the third one, we don't have a plot for that, but there was an attempt by the Arecibo Observatory to take a look at it.
Okay.
But since this is so small, this object is very small, it didn't quite observe it. Okay. If it were metallic, it was just on the edge of the signal to noise ratio was just on the edge of observation. And if it were metallic, something like a rocket booster, it would have gone. It would have gone over the detection threshold. So okay. This is the non-detection is important in this case to ensure that this is actually a. So we have three separate pieces of evidence, and we can definitely show that this is. We're quite certain that this is a real body, and this is only the second one detected in 14 years.
Cool.
So just a second. If we go a little higher, let me see just if I missed something. Yeah, so there's the table, and I think, yeah, that's the explanation about what I just said. Yeah, and here in this, we describe the observations and the methodology. But maybe maybe we can go then back lower just for the results. Back to, sorry. Yeah, and then the figure B shows that this is the fit of the so-called HG function, which is the asteroid. It is a phase function based on the phase angle. So this is the angle between the sun, the asteroid, and the observer. And we didn't really observe it at small phase angles, which is usually the area where it is kind of decided. So but we can see that it is slightly better for PCD than S-type. So that's another. It also shows that's better. So it's another independent assessment that it is. It's a silicate. On the bottle panel, asteroids C and D. Sorry, not asteroids. Images C and D. We then, now that we know that's an S or a V, and we know the area to mass ratio, we may work. This is part made by Davide Farnocchia. That is the Monte Carlo values for the geometric albedo, and then we try to assess what would be the density of these objects. So on the x-axis, the albedo values are embedded with the area to mass ratio, and then the density is derived, and the histogram is showed in D. So now that we know, that's actually, without any prior knowledge, if you take a look, the V types are actually a better match than the S type, but the S type is okay too. So yeah, and these values are consistent with literature values for the S and V types.
So when you're doing these Monte Carlo, the scatter plot in Monte Carlo space, what is it that's being sampled? Is this the uncertainty in the orbit, or is this the uncertainty in, what is it that's being randomly sampled here to generate the Monte Carlo?
So here we sample the possible albedo values. So
got it.
There are different.
Yeah.
It's you can't say that it's exactly 0.4 for V types. It's a spread, and it's shown then.
Okay.
Okay. So yeah, that's our object. It's, like I said, 1.2 meter in diameters. It's a silicate, and its density is consistent with that, with being a silicate. So it's a rock.
Yeah.
We see we see many of these, for example, on top of on Asteroid Ryugu and the boulders. So
cool,
something like that, a free floating analog of a boulder. So let's move on. The next plot is a rotation rotation period derived by Nick Moskowitz with the Lowell Discovery Telescope. So on the bottom panel is a folded rotational light curve, and it is, the colors represent, if you put them in a rainbow-like sequence, you would then get how they're really arranged. Then the mid panel is the Fourier analysis, and the top plot is the Lom's-Cargill.
power.
Power spectrum. Yes. So we know that the rotational period is 0.05. That is like 3 minutes 10 seconds. So what we can, this is perhaps the rotational period is perhaps the largest mystery that's remaining for this object, because we kind of expected that it to be rotating even faster for an object of that size based on predictions. So we would need to, that's some avenue to explore how the smallest asteroids really rotate, how fast, what's their real distribution in rotation periods. Okay.
Yeah, I'm with you. Yep. Okay. Good.
So let's then go on to the. So what does it in the text? Yeah, this is explaining the physical calculation, and then we go to the orbit. This is work then by Shantanu Naidu and David Farnocchi and Marco Micheli. And yeah, let's take a look at, for example, let's first take a look at the B panel. Okay. So this shows a sample of Monte Carlo orbits going back in time, and this is their accumulated. This is the number of captured samples. There is 1,000 orbits, and you see that in 2000, just before the end of 2018, there is a huge drop. So this corresponds to the date of September 15th, 2017.
Okay.
This is the date when there was a close event with 2020 CD3 with the moon.
Okay.
So over 97% confidence this object was captured on that date. However, some orbits, as you can see then from these are if we go back to A on the left hand side, so these are the blue ones, the blue on the top, the crooked, like the crescent thing, where are the blue samples. They represent the objects that are the ones that are captured. Then the green ones below the circle, these are the ones that they're the ones that remain before the capture. That means that this could have been captured for a longer time.
Okay.
But then the red ones, are, and the black circle is the moon. So there are actually some orbits originate from the moon. So this could have been an object ejecting from the moon.
Yeah.
We discuss a little further why it's probably not the case, but it's just interesting to see that at this point they are quite. With this only we cannot really rule it out. And yeah, so, and then if we look at C, this is now a little detached, but we can. But when we saw that this has been captured for 2.7 years, so from the 15th of September 2017, and then it was released from the Earth Moon system on, I think it was March 2020. That makes it 2.7 years.
Right.
And when we went back to simulations, and we took a look at how in simulations would it look, the average capture time of minimoons, it was not only 9 months. So this is an exceptionally long capture time.
Yeah.
So, but there was that clue that it was close to the moon. So we then mined the simulation data and took a closer look of these close approaches to the moon, and then we see that if an asteroid, a minimoon, has a close approach to the moon, so you can see on the x-axis that there's a minimal distance from the moon, and the more you go to the left, the closer you go to the moon, and then there is the capture duration is the y-axis. So there is a, if you go closer than 30,000 kilometers, that you can see that there is a correlation between the close approaches to the moon and the capture duration. So that's kind of an explanation that because it went close to the moon, it was captured for quite a long time. So it kind of maybe goes a little deeper into the gravitational well.
Cool.
Right. So let's maybe go on. Yeah, and here we also explain why this cannot really be a lunar ejecta. That's not the plot. We'll take a look at the plot in a second, but Bill Botke and Robert Jadeke, they explain that in order to produce a crater, an event to eject an asteroid of the size of a meter, we would require an event that would produce a crater on the order of kilometers. Okay. And we would definitely have seen it. That's essentially the very basic of it. And if we take now the second to last figure in this image, which is figure 5. So this is a question we ask ourselves: is okay. There are these close approaches of 2020 CD3. It made 11 orbits around the moon, around the Earth. So could we have seen it before? Okay. So it was discovered by the Catalina Sky Survey, and this is what we are taking a look here. So the x-axis is the days since the most probable capture time, and then we have the limiting magnitude of the Catalina Sky Survey is around 21st. There is the gray band represents it. Yep. So it's plus minus 0.5 magnitudes. Depends a little on the scene, a little on the moon phase. So it's we can't. It goes a little around the night. So, but essentially it's within that gray band. And then the points that we see there are the apparent magnitudes of 2020 CD3. So the red ones are the brightness, like the real apparent brightness of 2020 CD3, and below and of course the magnitudes in astronomy are weird. So the smaller it is, the brighter it is. So on the bottom it's brighter, and then the higher go, it's it's fainter. So you can see that if you just take a look at the red points, which go on several occasions below the threshold of the Catalina Sky Survey, we would imagine that we would have seen it at least on 6 or 7 occasions. Mm-hmm. However, if we take a look of how that image would look on a pixel, so we take into account the trailing losses, because when the asteroid comes close to the Earth, it makes a trail on the CCD, mm-hmm. and the signal is smeared over several pixels, right. And that essentially reduces the signal. So the real thing that we should worry about in this case is the magnitude, which is subtracted with the trailing loss. So these are the blue points. Okay. Got it. And when we take a look at the blue points, we can see that there is only 2 occasions. One is around 580 days, yes, and then the second one is 880 days, which is when it was discovered. So there would have been only one with the Catalina Sky Survey, which is one of the 2 most efficient asteroid discovery surveys. The other one is Pan-STARRS. So it would have been detected only on there was only one other opportunity to see it, and it's kind of give or take of how it goes there. So
Mm-hmm.
That's
Interesting. Okay.
yeah. So that's we took a look, and we were relieved to see that, well, in the sense that, okay, we didn't do anything wrong, but because it's quite hard. But then it's a little disappointing that it makes the trailing loss things makes these things even harder to detect.
Indeed. Yes. Okay. Minimoon.
Right. So that's when then we also discuss a little on the Minimoon population.
Mm-hmm.
So at any given time, an asteroid the captured asteroid has a diameter of around 75 centimeters, and an object of 3 meters is captured once every 10 or 20 years.
Okay.
So the fact that 2020 CD3 was discovered is kind of along the lines what we expected. So it confirmed the theoretical predictions, and it's so what implications does it have? Maybe talk it. It has well, like positive applications for the upcoming Vera Rubin Observatory's legacy survey in space and time.
Mm-hmm.
We expect LSST. We expect to find many more mini moons with LSST, and
What is once a mini moon is captured, what is a typical lifetime? Just thinking of the analogy to SL9, right? It didn't last forever in that orbit. So I'm curious what the lifetime roughly. It might be mass dependent. I can think of all kinds of things why that might be a wide range.
so
But I'm just curious what the number is roughly.
so it's around 9 months on average. There are
Okay.
like this one. It was for 2.7 years, and the previous one was captured around a year. So the two ones that were discovered are captured for a longer time than we expected, but that's maybe also due to this bias of things that there are the occasions to see they're quite rare. So, but 9 months is the average period according to simulations.
Okay. All right. Cool.
Yep. Maybe just let's just take a quick look maybe at the appendix figure, which is a little below. It's just out of curiosity, yeah, this one. Yeah, so out of curiosity, we took a look at, or Shantanu Naidu took a look at where, if the mini-moon originated from the moon, which part of the moon would it have originated from?
Okay.
So this is uh, like the entire surface of the moon. If assuming it's a sphere, approximating it as a sphere is taking a look at, and then the white circle in the middle is the face facing us, and the black thing is like the dark side of the moon. That is. So essentially, and the red points are the ones that it would have originated from. So essentially, it would have been on the dark side of the moon,
Mm-hmm.
facing us, and it would have been an event that would have produced a kilometer size crater. So that would have been very bright,
Indeed. Somebody would have.
but nobody, but nobody reported anything. So
Right.
yeah. Okay, so that's the plot, and I think that's so. Just to conclude, we showed that 2020 CD3 is definitely a natural object. It's been captured for, most likely it's been captured for 2.7 years, and that this confirms that our models are more or less right, and that ensures that with LSST, we could find many more.
Cool. Very nice. So you pointed to a couple of future and near future efforts. So if you want to look in your crystal ball and what might happen over the next 5 years or so, do we keep tracking CD3? How many of these might we expect to find with the Vera Rubin telescope, etc.? So just sort of, give a little future look on what you see on the horizon for the next 5 years or so.
Okay, so 2020 CD3 is unfortunately now out of reach of our telescopes. And it has been so since the summer, and it won't be coming back to Earth until maybe, was it 20? I think it was 2044, which was so.
Okay.
It's but regarding the other mini moons, so yes, we do expect LSST to find many more of these, but we have a, so to say, a good scenario and a bad scenario. So if we start with a bad scenario, we maybe expect to find maybe once a year, once every second year, and a good scenario would be maybe once every 2 or 3 months. But that depends a little on the linking efficiency software and that kind of stuff, which brings me to what would the future lie in. So for Minimoons, that was one essential task would be to assess the linking efficiency and perhaps even building a separate pipeline for processing Minimoons for LSST, because they're a little peculiar. They don't really fit with all the other solar system objects because they are so fast and they're rocks. They're like rocks, but rock stars. They shine bright and then they fade away.
That's a great analogy. Very good. Grigori, I want to thank you so much for spending some time and walking us through your lovely AJ paper.
Thank you for inviting, and for those who are watching this, then have a happy Christmas and a happy New Year.
Good solstice. All right, everyone. Thank you so much. We'll see you on the next one. Bye-bye.